Logistic regression is a specialized form of regression that is formulated to predict and explain a binary, two-group categorical variable rather than a metric-dependent measure. Logistic model was originally developed for use in survival analysis, where the response y is typically measured as 0 or 1, depending on whether the experimental unit survives. Example of typical binary coding is 0 for negative outcome, when event did not occur, and 1 for positive outcome, when event did occur. Logistic regression may be described as estimating the relationship between a single non-metric binary dependent variable and a set of metric or non-metric independent variables. Note, it does not require any specific distributional form of independent variables, and the issues such as heteroskedasticity, recalled from the previous lecture, do not come into play in this analysis. Moreover, logistic regression does not require linear relationship between the independent variable and the dependent variable. Our standard linear model has expected value range from -infinity to +infinity. So we need to limit the range of our prediction to the range between 0 and 1. We can use exponential function and logit transformation to do so. Multiple regression employs the method of least squares, which minimizes the sum of squared differences between the actual and predicted values of dependent variable. The nonlinear nature of logistic transformation requires another procedure, known as a maximum likelihood procedure. Logistic regression measures model estimation fit with the value of -2 times the log of likelihood value, referred to as -2LL or -2 log likelihood. Thus, the lower the -2LL value, the better the fit of the model. And just like in the multiple regression, the logit R-square value ranges from 0 to 1. As the proposed model increases model fit, the -2LL value decreases, and the perfect fit will have a -2LL value equal 0 and R2 square logit value equal of 1. So instead of minimizing the squared deviation, least squares, logistic regression maximizes the likelihood that the event will occur. But how do we predict group membership from the logistic curve? For each observation, logistic regression technique predicts a probability value between 0 and 1. Thus, the predicted probability is based on the values. If the predicted probability is greater than 0.5, then the prediction is that the outcome is 1. Otherwise, the outcome is predicted to be 0. The event did not happen. Let's compare logistic regression with classification problem in machine learning, and you'll see that both are very similar. Classification with a set of observation of 2 or more discrete categories is a central task in machine learning. And if you look at classic supervised learning settings, we have data points that are presented by a set of features, discrete or continuous. The training data also have a label indicating the class of data points. A model is fitted on the training data, and the trained model is used to predict the class of unseen data points. So logistic regression has the same settings, except that machine learning make an emphasis on predicting the class of unseen data, while in logistic regression, the emphasis is placed on the significance of the effect of the features or independent variables. In fact, logistic regression is a standard technique in machine learning, sometimes known as maximum entropy. Logistic regression is a part of GLM, generalized linear model, where the expected value of the dependent variable is modeled via link, the link function. There is a large family of link function, binomial, Gaussian, Poisson. For the normal family, and this is the focus of this lesson, the response can be specified in one of 3 ways: as a factor, as a numeric vector with value between 0 and 1, as a 2-column integer matrix, where the first column gives numbers of successes, 1s, and the second number of failures, 0. Let's build our workflow for logistic regression analysis. First, we explore dataset. In this case, example coming from breast cancer Wisconsin dataset. Instead of the file name, this time we enter a complete URL of a file from the website repository. We'll use names function to set the names of the dataset, as the actual dataset did not come with the header names. Let's start by checking dataset using string function. This function provides a compact display of internal structure of our object, and we can see that we have a value equal to question mark, which is indicator that we have a missing attribute value, so we need to remove them before regression analysis. After that, we need to convert our variable, and we need to make sure all our variables are integer values. To obtain a brief summary of dataset, we can use summary function. This function returns a set of statistics for each variable. To get the number of cancer cases for each classes, we have two classes, we can use table function, and this function uses the cross-classifying factors to build a contingency table of the count for each combination of factor levels. So we have 2 for benign and 4 for malignant. So we have 444 cases for benign class and 239 cases of malignant classes. However, for GLM function, we need to replace them by 0 and 1s. In step 4, modeling, let's remove observation ID, since this is not a useful variable. Logistic regression is called by imposing the family type. In this case, family is binomial with the link logit. The class ID code means that we want to create a model that explains the class variable, our response, depending on all other variables except ID. Finally, let's look at the model summary. First, we see the deviance residuals, which are a measure of model fit. It shows us the distribution of deviance residuals for individual cases used in the model. We also see that not all coefficients are significant, with a p-value less than 0.05. Logistic regression coefficients give the change in the log odds of the outcome for 1 unit increase in the predictor variable. We find 5 variables statistically significant. Null deviance indicate the response predicted by model with nothing but intercept. The lower the value, the better the model. Residual deviance indicates the response predicted by model on adding independent variables. Again, the lower the value, the better the model. Deviance is a measure of goodness of fit of our GLM model. The analogous metric of adjusted R-squared in logistic regression is AIC. Alkaike information criteria is the measure of fit, which penalizes a model for the number of model coefficients. Therefore, we always prefer model with a minimum AIC value. And finally, the number of Fisher scoring iteration is returned, and the scoring is a derivative of Newton method for solving maximum likelihood problem numerically. For our model, we see that Fisher scoring algorithm needed 6 iterations to perform the fit. We can use the model to make predictions. To do that, we will use the predict function. In this line of code, we apply predict function to the previously built logistic regression model, passing the entire set of data. The results are rounded off using the round function, and now we can count the cases, 440 for 0 and 243 for 1. To analyze the performance of the model in this classification, we can calculate the confusion matrix. In the confusion matrix, our classification results are compared to our real data. So in this matrix, the diagonal cells show the number of cases that were correctly classified. All the other cells show the misclassified cases. To view the confusion matrix, we can use table function. You notice 20 arrows, 8 for false negative and 12 for false positive.